So we are doing problems from chapter 17. Okay, this problem says the displacement of air molecules in sound waves is modeled with wave function sxt equal to 5 nanometers. Cosine kx, so there's the wave number, omega t. Okay. So you saw that in a sound wave, as the wave travels in this direction, an air molecule will oscillate back and forth like that. And they're giving you this amplitude is 5 nanometers. Okay. The size of an atom or a molecule is roughly 1/10 of a nanometer. So this is 50 atoms worth. Okay, so if an atom is as big as your fist, it's oscillating like that. Okay, that's actually a fairly intense sound. Okay, so again, so SXT. So here's the standard forms: sine or cosine function, cosine kx minus omega t. And so for your function, this is 5 nanometer cosine. Now you guys remember that the argument of a cosine function is dimensionless. Okay, so this has units of meters, this will have units of inverse meters. This has units of seconds, that'll have units of inverse seconds. Okay, this argument is dimensionless. All right, so cosine kx 91.54x. So there is k, and I'm not writing units because we'll say this is in meter. Okay, so this is in meters and that's in inverse meters. And minus 3.14 into 10 to the power 4 t. So this is omega. Okay. So now we'll have to, from this equation, we'll find various parameters associated with the wave. Okay. So what is the wave speed of the sound wave? The wave speed is omega by k, which is also equal to frequency times lambda. Okay, so this is 3.14 into 10 to the power 4, 1 over second, divided by 91.54, 1 over meter. And the meter will come to the top. It's that divided by that, meters per second. Okay. All right, so .14 343 meters per second. All right, and this is the speed of sound in air at room temperature at 20 degrees Celsius, okay, which is the temperature here. Okay, part B says, what is the maximum speed of air molecules as they oscillate in simple harmonic motion? Okay, so the air molecules are oscillating in simple harmonic motion. Think of a mass attached to a spring. When will these air molecules be going the fastest? I'm sorry? at the center. So just like, okay. And what you want to do is, so this is the displacement of the air molecule. And to find its velocity, what you do is you take the derivative of this with respect to time. Since this is a function of two variables, you take a partial derivative of that with respect to time. Okay. So this is the wave velocity, that's the speed at which the disturbance is traveling. That speed is different than the velocity of the air molecule. Okay. So the speed of the atom, so this is the wave speed. The speed of the atom or the molecule is del S by del T. Okay, so take the partial derivative of that. And so that is A, derivative of sine is minus, cosine is minus sine, kx minus omega t. And using the chain rule, that would be the derivative of this guy, the argument, which is, then you get a minus omega. Okay, so this velocity of an atom is A omega sine kx minus omega t. And the maximum value would correspond to sine equal to 1. Okay, so this value being equal to 1. So this maximum speed will be when the atom is in the middle, and the minimum speed, which will be 0, is when it'll be at the extreme. Okay. So max is A omega. The amplitude of the wave is 5 nanometers, and omega is 3.14 into 10 to the power 4, 1 over second. Okay. So V atom max is 15.7 into 10 to the power 4 nanometer per second. All right, so what we'll do is we'll make this 150, okay, we'll make this 0.157, that becomes 10 to the 10 to the power 6, and then nano is 10 to the minus 9, so it'll become 10 to the minus 3 meters per second. 0.157 millimeters per second. Okay, so that is the speed of the atom. And it might not sound a lot, but that's a single atom, and that's very fast for it. Okay. The molecule is oscillating. It's going at 1/10 of a millimeter a second at its fastest. Okay. And then they ask you, what is the magnitude of the maximum acceleration of the air molecules as they oscillate? So as the air molecules are oscillating, at the center, they're going the fastest. Where is their acceleration the maximum? So think of the air molecules as a mass attached to a spring. That's what's happening. So where is the mass, where is the acceleration of the mass the maximum?
At either end.
At either end. Okay. Remember Hooke's law. Hooke's law says the force is minus kx Okay. The force is given by minus kx. So when x is largest, force is largest, and the acceleration is largest. Okay. So at the extremes is when the acceleration is the maximum. All right. So what is the magnitude of the maximum acceleration? Okay. Again, acceleration of the atom is given by del s square by del t square. The second derivative of the displacement of the atom. Okay. We already have the first derivative, and now we will take the second derivative. Okay, so derivative of this, derivative of sine is cosine, and then you get a minus omega again from there. Okay, so acceleration del v atom by del t, which is del t by a omega sine kx minus omega t, and so derivative of sine is cosine, and then from chain rule, when you take the derivative of that, you'll get a minus omega. Okay, so you get minus a omega square cosine kx minus omega t, and a max will correspond to a omega square. Okay, the sign just telling you the direction of the acceleration. Okay, so when the atom is here, which direction is the acceleration? I'm sorry? When the atom is here, the acceleration is in that direction, and when the atom is here, the acceleration is in that direction. Okay? Okay. So again, 5 nanometers, and omega is 3.14 into 10 to the 4 1/2 square. Okay, 4.9 times 10 to the 9 nanometers per second square. Look at this number, nanometer. Nano is 10 to the minus 9, which cancels that. So the acceleration, so the maximum acceleration is 4.9 meters per second square. That is 0.5 Gs. Okay, so the maximum force on the atom is half its weight. Okay, so all right, that's what's going on in this problem. Okay, so again, what the problem was about was from the waveform, you can get all kinds of information. You can get the velocity of the atoms, you can get the velocity of the wave, and so on. Okay, so that was the point of the problem. Okay, so this problem says bats use sound waves to catch insects. Okay, so we saw this in lecture on Monday. Bats use ultrasonic waves to navigate. So a bat will send out ultrasonic waves. So here's a bat, and here's an insect, and these ultrasonic waves bounce back. Okay. And from the intensity of the reflected wave, they know the size of the bug. Okay, they get, and if the bug is moving toward them, the reflected wave has a higher frequency than the incident wave, and so on. Okay. Now here's an interesting story. Okay. So these are sound waves, and if you use a sound wave of wavelength lambda, the smallest bug you can see, so you can't see this bug because this bug is too small. It's smaller than the wavelength, so you can't see this bug, but you can see this bug. Okay. Now the velocity of the wave is frequency times wavelength, and you see higher the frequency, smaller the wavelength. So higher the frequency a bat uses, smaller the wavelength, smaller the bug it can see. Okay, well, it can see big bugs too, but it can see small bugs. So it can eat these small bugs, but a bat using smaller frequency cannot see these bugs, so it has exclusive dibs on those little bugs. Okay. So in nature, you see this. Bats that use higher frequency for echolocation tend to be smaller. And small bats and big bats can live in the same neighborhood because they're eating different sized bugs. Okay? By using different frequencies, you adapt to different forage. Okay? All right. Anyway, bats use sound waves to catch insects. Bat can detect frequencies up to 100 kilohertz. If the sound waves travel through air at a speed of 343 meters per second, what is the wavelength of the sound wave? Okay, so the problem itself is fairly simple. V is frequency times wavelength. A 100 kilohertz. Hertz is 1/seconds, so okay, so 3.43 into 10 to the minus 3 meters, 3.43 millimeters. So this bat is eating 4 millimeters is about that much, okay? So about that big. So these bats are eating bugs about that big. Yeah. So like I said, the higher the frequency they use for echolocation, the smaller the bat. Yeah. What is the speed of sound in a medium where 100 kilohertz frequency produces a 5.96 centimeter wavelength? What substance is it likely to be? Okay, so speed is frequency times wavelength. 100 kilohertz times 5.96 centimeters. A centimeter is 10 to the minus 2 meters. So that gives you 1,000 times that. So 5.96 into 10 to the 3 meters per second. Okay, 6,000 meters per second, 6 kilometers. So, okay, so it's, oh, there it is, steel. Okay. So the stuff through the medium is steel. Okay. Okay, this problem says the density of a sample of water is 998 kilograms per meter cube, and the bulk modulus is 2.15 gigapascals. what is the speed of sound through this sample? Okay, so this is for longitudinal waves. So for longitudinal waves, the speed is given by bulk modulus for longitudinal waves, and for transverse waves, the speed is given by shear modulus divided by density. Okay, so our speed is, the bulk modulus is 2.15 gigapascals, 10 to the 9 pascals, which is Newton per meter square, and the density is 998 kg per meter cube. Okay, so the speed will work out to, okay, so what we'll do is we'll divide by 1,000, that's 10 to the 6. Square root of that would be 10 to the 3. So 10 to the 3 meters per second. And then this, what will be left is 2.15 divided by 0.998. Okay. Okay, so it's the speed of sound in water is 1,500 meters per second. And the speed of sound in air is 340 meters per second. So in water, the speed of sound is almost 5 times that in air. Okay. Okay, this problem says the warning tag on a lawnmower states that it produces a noise at a level of 91 decibels. What is this in watts per meter squared? Okay, so they give you the sound level in decibels and they want you to find the intensity of the sound. And if you check your notes, the two are related like this, log I over I naught. So this is the intensity and that's the sound level in decibels. I naught is the threshold of hearing, and that's a constant. And for humans, I naught is 10 to the minus 12 watts per meter squared. Okay. So in our problem, the decibel level is 91 decibels equal to 10 log I over I naught. So 9.1 is log I over I naught. Okay, so now so what this means is I over I naught, this is to base 10, so 10 to the power of that is 10 to the power 9.1. So I is 10 to the power 9.1 times I naught. All right, and if you use your calculator, this works out too. .26 milliwatts per meter squared. Yep. Okay, again, this is the intensity and there's the decibel level. Okay, this problem says an 8-hour exposure to a sound intensity level of 90 decibels may cause hearing damage. Okay. So why do you consider problems like this? So if somebody is working in a construction site and using a jackhammer all day, you can damage your hearing and stuff like that. You could be a rock star, you practice a lot and damage your hearing. Okay. So what we'll find is what energy in joules falls on a 0.8 centimeter diameter eardrum as so exposed. So we are going to find out how much energy is fallen on your eardrum over this period of 8 hours. Okay. So again, we will first find the intensity. We will first find the intensity and then calculate the energy. Okay. So 90 equal to 10 log I by I naught. So 9 equal to log I by I naught. 10 to the 9 equal to I by I naught. I is 10 to the 9 I naught equal to 10 to the 9 into 10 minus 12 watt per meter squared. I is 10 to the minus 3 watts per meter squared. Now intensity is power over area. Power is energy over area, energy over time. Okay. So intensity is how much energy fell on per unit area in this much time. Okay. So the total energy that fell on the eardrum is the intensity of the sound times the area of the eardrum times the time over which it fell. Okay. The intensity was 10 to the minus 3 watts per meter square. The area, the eardrum is circular. Radius is 0.4 centimeters. 0.4 into 10 minus 2 pi r square. And the time is an 8-hour exposure. 8 an hour has 3,600 seconds. So watts is joules per second. The second cancels. Watts is joules per second. The second cancels. And there's a meter square which cancels with that. So this will work out in joules. Okay. All right, let's take your powers of 10. That is, we'll make this 4, 10 to the minus 3. That's 10 to the 6. And then another 10 minus 3, that's 10 to the minus 9. And there's 10 to the 3, so that's 10 to the minus 6. Pi times 16. 4 square is 16. Then times 8 times 3.6 joules. All right. So this works out to, let's see. So 1.45 into 10 minus 3 Okay, that's a millijoule. Okay, well, what does this mean? This is the amount of energy falling on your eardrum if you, let's say, practice rock music for an 8-hour day, or you work with a jackhammer for an 8-hour day. Okay, so energy is mgh, g is 10, okay, and so this is a millijoule. So if you take a gram is 10 to the minus 3 kgs. That's 10, and if you, so 1.5 into 10 minus 3 kgs times 10 times 0.1 meters. So it's like 1.5 grams falling from 10 centimeters onto your eardrums. That's the energy falling on it. Okay? Okay, so this problem says loudspeakers can produce intense sounds with surprisingly small energy input in spite of their low efficiencies. You guys remember loudspeakers have efficiencies of about 1%. What does that mean? If you put in 100 joules of electrical energy in a loudspeaker, in a speaker, only 1 joule is converted into sound. Okay? So only 1% of the energy put into a speaker is converted into sound. The other 99% is converted into heat. It goes wasted as heat. Okay? So this problem is pretty amazing. Loudspeakers can produce intense sounds with surprisingly small energy input in spite of their low efficiencies. Calculate the power input needed to produce a 90 decibel sound intensity level for a 12 centimeter diameter speaker that has an efficiency of 1%. This value is the sound intensity level right at the speaker. Okay? So you want to produce a 90 decibel sound right at the speaker. Okay? You're right next to the speaker. And so this is where you're listening. Okay? And so 6 centimeters is the diameter, is the radius of the speaker. And you're listening right there. Okay, so beta is okay. So I'll go through this calculation fairly quickly. We've done this several times. What we're doing is we're finding the intensity of the sound wave. So 9 equal to log I over I naught. I is 10 to the 9 times 10 to the minus 12 equal to 10 to the minus 3 watts per meter square. Okay, so the intensity of the sound you're producing right next to the speaker is 10 minus 3 watts per meter square. Okay, so what you're going to do is you're going to find out how much electricity, what is the wattage of the speaker. Okay, so what is the power of the speaker? So intensity, the sound intensity is power of the speaker divided by the area. Okay, and the area, it's a circular speaker, so pi r square. So power of the speaker is intensity times pi r square, 10 minus 3 watts per meter square, pi, radius is 6 centimeters. So this is the power in sound. Okay. And so this is 10 to the minus 4. That makes it 10 to the 7. 36 times that. So watts. Okay. So, but they tell you that the speaker is 0.1 efficient. Okay, 0.1% efficient. So the power in the sound is 0.01 times the power of the speaker. Okay, or that's how much electricity you're feeding the speaker. Okay. So the wattage of the speaker. Yeah. So the wattage of the speaker is 0.01, which is 11.3 into 10 minus 6 watts divided by 0.01. Yes, so this is 11.3 into 10 minus 4 watts equal to 1.13 milliwatt. So what we are saying is you can have a milliwatt speaker. If you put your ears right next to the speaker, it'll produce a 90 decibel sound. Okay. Even though it's only 1% efficient.
Is that why they don't work harder to make it more efficient?
No, well, that's, you want more efficiency, I would imagine you have to make the air denser. It's got nothing to do with our electronics. It's got to do with the medium here. It's got to do with the coupling. So, well, okay, you can go home and look it up. Sonar, which is producing sound waves underwater, there it couples to the water better. So that'll probably be much more efficient. Yep. Okay, what is the fundamental frequency of a 0.672 meter long tube open at both ends on a day when the speed of sound is at? What is the frequency of its second harmonic? Okay, so if you have a pipe open at both ends, so this could be a flute, and the fundamental frequency is the lowest frequency you can produce, lowest frequency sound you can produce. And for a pipe open at both ends, you are producing this is the fundamental mode. That is, you have an antinode at the end, a node in the middle. This is the lowest frequency you can excite. The next higher frequency, the next mode, so is this one. Okay, so this is the fundamental, and so these are the allowed frequencies. You can check out on the notes. So here's the pipe open at both ends, and the loud frequencies are N. All the harmonics are allowed. V divided by 2L. So the allowed frequencies are N, V divided by 2L. So the fundamental corresponds to N equal to 1. Okay, so the speed of sound is the speed of sound is 344 meters per second, and 2 times the length of the tube is 0.672 meters. So this frequency and the second harmonic F2 is 2 F1 to 512 hertz. Yep. So the second harmonic is n equal to 2. Okay, this problem says a piano tuner uses a 512 hertz tuning fork to tune a piano. He strikes the fork and hits a key on the piano and hears a beat frequency of 5 hertz. Okay, so he's playing this tuning fork and he's playing a key on the piano. So the beat frequency is given by F1 minus F2. Okay, the beat frequency is when you play two sounds of frequency close by, you hear a beat frequency whose intensity goes up and down by a frequency equal to the difference in the two frequencies. Okay? That's how musicians tune their instrument. So, and then what they do is they try to change the frequency of the instrument so they don't hear any beats. Okay? So what the piano guy is trying to do is he's trying to tune that key to that frequency. Yep. He tightens the string of the piano and repeats the procedure. Okay. So the velocity of the wave on a string is tension divided by mu. And the velocity is frequency times wavelength. So that's on the piano string. So if you tighten the string, the wavelength is constant. That depends on the length of the string, which is not changing. So the frequency is increasing. Okay. He tightens the string of the piano and repeats the procedure. Once again, he hears a beat frequency of 5 hertz. What happened? So what happened was, so initially, the frequency on the string was below the frequency of the 512 hertz. It was 507 hertz. He tightened the piano string, and the beat frequency was the same, 5 hertz. And now, on the piano string, it's higher than the 512 hertz. So the frequency of the string went from 507 hertz to 517 hertz. Okay? That's what happened. All right, so he had to increase the tension by, let's say, 10 pounds. He increased the tension by 20 pounds. Well, not quite. I mean, it's the square root, so, but that's what happened. Okay? All right, this problem says, at an air show, a jet flies directly towards the stands at a speed of 1,200 kilometers per hour. Okay, so a jet is flying towards the stands. So here are the stands, and here's the jet flying towards the stands. All right, so it'll emit a frequency, and since these are the observers, the jet is flying toward you, what you hear is a higher frequency. Okay, that's the Doppler effect. It's emitting a frequency of 3,500 hertz on a day when the speed of sound is 342 meters per second. what is the frequency received by the observers? Okay. So if you check your notes, the observed frequency is v, the speed of sound, plus observer's velocity, v minus vs, times the emitted frequency. Okay. And again, there are sign conventions associated with this. These guys are positive if the observer is moving towards the source or the source is moving toward the observer. And when the source is moving away from the observer, then that would be negative. Okay. So what is the frequency received by the observer? So for the first case, okay, so the velocity of the source is 1200 kilometers per hour, meters, and 3.6 into 10 to the 3 seconds. So velocity of the source, the velocity of the plane in meters per second. Okay. All right. So okay, the frequency of 3,500 hertz emitted by the plane, the frequency these observers hear is v is the speed of sound, 342 meters per second. V naught is 0. The observers are at rest. 342 minus 333.3 times f. Okay, you see, if the plane were flying faster than the speed of sound, this would have no solution. If it's flying faster than the speed of sound and moving toward you. Okay. All right. So that's 344 8.7. Okay. Okay, so 40 times the frequency. Okay, so 39.3 times 3,500 hertz. Okay, so the frequency you hear is 40 times the frequency emitted. Okay, so can you hear this frequency? Of course not. But if a plane is flying toward you, you do hear it. So what's going on? So the frequency got multiplied by a factor of 40 at that speed. So a 20 hertz frequency would be heard as 800 hertz. Okay. So all the low frequencies, the infrasonic frequencies, will get to your hearing range. All the high frequencies will be in the ultrasonic range, which you can't hear. Okay. So what frequency do they receive as the plane flies directly away from them? Okay, so now here the observer and the source is flying away. F prime is v, again observer speed is 0. V, now with the source flying away, that velocity is negative. Okay, so We'll get to that in a second. Okay, so the speed of sound is 342 meters per second. 342 meters per second. This frequency is 3,500 hertz. Minus 333.3 meters per second. Okay. So now this is 342 divided by 775.3 hertz. Now you can hear this frequency. Okay, so now it's 1500 hertz. So once the plane flies by you, all the frequencies are reduced by a factor of half. Okay. Okay, last problem. This problem says an airplane moves at Mach 1.2. What does that number mean? Yeah, so 20% faster than the speed of sound, okay? And produces a shock wave. What is the speed of the plane in meters per second? What is the angle of the shock wave? Okay, so part A, Mach number is equal to speed of sound divided by speed of plane. Okay. So, the other way. Okay, so what is the speed of the plane? Speed of the plane is 1.2 times the speed of sound, 343 meters per second. On the exam, you'll take the speed of sound as mostly 340 meters per second in most of the problems. And if you want to convert that to kilometers per hour, you just multiply it by 3.6. It's 1,482 kilometers per hour. And if you want to convert that to miles per hour, divide that by 1.6, 926 miles per hour. Okay, and the shock angle, okay, so this is the shock wave, and this shock angle is given by, okay, the faster the plane is flying, smaller this angle will be. Okay? And so sine theta is velocity of sound divided velocity of plane. Okay? So you get a shock wave when an object is flying faster than the speed of sound. Okay? So this has to be less than 1 for this to have a solution. Okay? So theta is sine inverse, and the speed of the plane was 1.2 times the speed of sound. Okay. Okay, so it's 56.4 degrees. That's the angle of the shock wave. Okay. All right, guys, so that finishes problems from this chapter.